Okay, so we were here, and the main idea here was this one, that have a color space. Have a color space. The attribute vectors, because these are the unique vectors in this direction. Then we have a point, and this point is absolute zero. Zero. We can express in some other way, and some other way be this one. This one in our example, but doesn't mean that it is the only way of changing the way we express the colors. This one, this is called RGB, so red, green, blue. This is hue saturation value, but there are many others. And here the main idea is that you separate into two parts. One that is luminance, that is related to intensity, so how many photons, and the other part that is the color. Color, luminance can give many different names. Okay, but one for intensity, two for color. This is the main idea. And the decomposition we did was this one. Okay, so you have the color hue, you have your point there. That is a line of gray values that go from black to white. Then this point is contained in a plane. Okay, so it is in this plane, and we look this plane for sure it has one gray value. That is this one here. It is the intersection between this line and this plane. So it has a gray value. And then we have to so this length is the value. Okay, so in the hue saturation value, the value is this length. So how separated the plane is from the molecule. And then we have to give the color. And the color is given by two elements. One is how far you are from the line, that is the saturation. The other one is in which direction you have to travel to reach that point. To specify that direction, so this one. So to specify that direction, you have to find a point in the plane. So this plane contains a gray point, a gray point, and a pure red point. So you join these two lines, these 2 points. You join those 2 points, and then you make a triangle between these 2 vectors. That is the hue. And we saw yesterday how to go from one to the other. These are the coordinates here. Happen here. So we have the hue saturation value. Value is the length of V. Saturation is the length of S. And then hue is the angle between the vectors. And so this given RGB, you can go to HSV and the opposite. So that is the but we can go in the opposite direction. So given HSV, so you know the expression of the color in the HSV coordinates that are these ones here. They are these ones. So these, and these are the coordinates of your color in the HSV coordinate system. And then you convert the RGB with the help of this matrix. So you simply have to multiply this matrix by the coordinates of the HSV. Here we have the coordinates in the HSV. Then you simply multiply and you are going back there. Any questions? Yes. So it's yeah, it is always that. colors. Doesn't mean that you have to learn the matrix by heart. Know that there is a big fix comparison. What is important is the meaning of this matrix. So the meaning is each one of the columns is a unit vector, and these unit vectors they go. So they go from HSV to RGB. And so this is the expression of E in the RGB coordinate system. This is the expression of what's this vector here. What's this one? The RGB coordinate system and the one perpendicular. Okay, so now you may remember yesterday we were doing this gamma transformation on the R, T, and B channels. So we will do something similar. So you can think of one of these planes, one of these intersections that we have, and when the value is 128, this is the intersection. And now we can decompose that into three channels. So red, green, and blue. And this is how it would look like. So this is the red region. So this is active. This doesn't need any red, so it is inactive. And the same everywhere. So this is the green region. This is active. This is inactive. So on. And now we can convert those red, green, blue values into HSV. So this is a plane. So that means that the value is all the time the same. So we have defined this vector, this plane, because it is R plus B plus B is equal to 384. So this is one of these planes that is perpendicular to the phase line. And the value is this one divided by 3, so it's 128. So that means that the value is all the time the same, all the time. For this plane, for these colors. Okay, so what about the saturation? Saturation is how far you are from the gray point. The gray point is in the middle. So saturation is how far you are from the middle. And then the hue is an angle between your color and red. So red is here. So if you are one of these colors, well, you have a very small angle. Then as you go away, the angle increases. Then increases, and at some point is maximum. So either you represent those colors in this way, red, green, and blue, or you can also represent the same colors this way. And you can put colors to the hue. This is a representation issue. So the hue is an angle. So it's only a value. You can put colors. Okay, so now let's do something similar to what we did yesterday with the gamma transformation, but now in the HSV screens. So we have an image, it's a histogram. Now we can increase the saturation by 50%. So take any one of these. So let's say that your color is this one. It's color, that means that this is your saturation. You have a saturation that is somewhere between 0 and 1. And this value you can multiply by 1.5. And so you're increasing the saturation. If you go away from the plane, you click, you stay at this. So you increase the saturation by 50%. And it is more simple. We compare the two. This one is saturated, this one is. And then we can, this is original, we can decrease the saturation. the more you decrease the saturation, in the limit, if you set all the saturation to zero, how would the image contrast? Be great. So you would be, so it is not a flat image, so it would be black and white image, but you would see the guys and so on. But it would be great, because you have no saturation. And then, this is again the original. Now we will play with the hue. So you have a color. Okay, so let's go back to our here. So you have a color. Let's say this one. This is the hue for that color. But this is an amp. So you can add this hue. You can add any amount of degrees. So let's say that you add 60 degrees. So now you go from this point to this point, or you may add 100 degrees, and then you are there, whatever. So you can add an angle to the hue. So we will do that. We will add 60 degrees to the hue. And then there is which is the result. And then there is this table here. Red goes to yellow, yellow goes to green, green goes to cyan. So that is it. So you are in red, you add 60 degrees. And now you are yellow. You are yellow, you add 60 degrees, now you are green. Green changes to cyan and so on. So this is the from here. Then you can have 120 degrees, you can have 180 degrees. We gave a name to this, adding 180. Those colors. Complementary. So the complementary colors. You can have 240, 100, 360. And yeah, so this is so far we have been showing the histograms of the red green blue channels. But also we can do this representation. So we will make a histogram traveling around the hue. So this is the hue. So you start 0 degrees, 60 degrees, 120 degrees, and so on. Now you make a histogram, the hue. You don't care about the saturation. It is the histogram of the hue. Okay, so this is the original histogram. When you add 60 degrees to the hue, everything shifts by 60. Everything shifts to the right, 60 degrees, 120, 180, and so on. Okay, any questions here? Okay, so then we will move to a different topic, somehow related. So let me show you what we will do. So let's say that this was an original image, but for some reason it has degraded, and you don't have this one, but you have any one of these. Okay, so the paper has degraded, and then the colors have changed. So can we go back from one of these images to the original? How do we do that? So we have to find correspondences. Okay. So this one. So let's say that this is our degraded image. This is the original. So we have to find corresponding points. And in these points, we have to say, okay, this is the value that you see in your degraded image, but the true value should be this one. Okay, so let's say, now look at the red, green. So the red and green, they stay the same. But the blue, this one has lost blue. So we have to restore them. So we have to boost the blue value. We go from 114 to 171. And You do the same for a few points. For this one, okay, the red and green stay the same, but the blue will increase it. This one, red and green stay the same, but the blue will increase it. So in general, is we have a couple of elements. Okay. And you have to make correspondences between colors. And then you say, this color here, this color here, this is a color. Okay, this is not a location, it's a color. This color corresponds to this one, EI. And because we will have many, then we put them and say EK1 here. Then you have to be the correspondence. Yeah, yeah. So you have to give the correspondences. Okay, so now what do we do with those correspondences? Go back. Okay, so we can think of transformations in this way. So let's say a gamma transformation. For a gamma transformation, we can write it this way. So you can take the original color, you apply a different gamma to each one of the channels, and then you get a new color. So in general, the path is this. So generally, what we have is that yeah. So you have an original color, you apply a transformation, but then you get a new color. And these are the RGB coordinates of those colors. T is a transformation, and we have given the example of a gamma transformation, but it can be whatever. Gamma is non-linear transformation, but we can think of linear transformation. So a linear transformation, in general, what is a linear transformation? That's here. Why do we say transformation is linear? So this is linear. Linear is and only T. We can listen. T and only T. T A one, that's B A B one, B B X two. This is the condition for linearity. And if this is a vector, all linear transformations, how can you write a linear transformation that operates on vectors? So this is again. But now we wonder what happens with linear transformation. If it is linear, I'm sure that I can write this transformation in some way. A matrix times the vector. So all linear transformations can be written by a matrix, can be described by a matrix. And this matrix, or let's say that this is 3D, this belongs so then this will be A11, A1, B, B1, B, A1, A5. So there are 9 numbers that describe my transformation. Okay, so E, if it is linear, I can write it in this way. Okay, good. So if it's linear, I can write it as a matrix operator. Okay, so let's think of linear transformation for crystal. Let's say that I apply scaling factor. So if I apply a scaling factor, this is my to the red channel. This is my matrix. So this matrix leaves unchanged G and E, but R1 R0 is transformed into R1. Okay, so this is a scaling of the red. And here in this particular example, we are making the red factor. So that means that the vector, so we had originally the vector that is here, and then we increase the red, but we leave here at 2 unchanged. So it is here. So we have this point, we increase the red, but we leave blue and green unchanged. So we are making the image more red. So we are making turning this color, this color. So you see, green and blue remain unchanged, and the red is a scalar. Can do the same with any one of the other channels. What we are doing is expanding the vector, the direction of the scaling. Expanding or compressing the vector, depends on whether it is larger or smaller. You have the three dimensions. Okay, so in general, we are interested in finding this matrix. So we have these correspondences. These correspondences here. And I wonder, okay, there must be a matrix. There must be a matrix that transforms. That transforms any color. Any color. Now it is not 0.1 or whatever, it's any one. It will transform the input vector, the input color, they are transformed through this matrix into this one. And I wonder, okay, which is this matrix? Find. So let's say you have a single point, a single pair. Okay, so you have, let's consider only one color. Okay. Okay, so then this equation, what is saying is right here. So it is saying this equation is for that particular color, let's say it's color 1. Color 1. The red in the is A11 times the red I A, the green that's A13, the blue I. This is for color 1. And then we have a similar equation with one, yeah, 1 red 1, say 2 green 1, I say 3. The same for the blue. Okay, 1, 8, 1, 1, 8. So if you give me just a color pair, so I have just one color pair. This is one of the colors in the output, and this is one of the colors in the input. So you just give me a pair, and you are giving me 3 equations. So for every color pair, you're giving me 3 equations. How many unknowns? Which are our unknowns? So I want to find the A matrix. So my unknowns are these coefficients. And so we have 9 unknowns, and I have 3 equations. So if you want to fully specify this matrix, you at least you need to give me three pairs. Three color pairs. Okay, so now you give me three color pairs. And this is a very convenient way of writing the equation system. So I will write the equation system in this way. So, okay. So you will give me three color pairs. This one, that is a column vector. You give me this second, is another column vector. That's another column. Then it is okay. The same back. So I can rewrite this just more compact form. I can say this is Pj. Now it is not a matrix, okay? A vector. These are, but if you put three vectors together, it is not a vector, it is a matrix. So I don't put the bar. So this is a matrix. One. If I want to solve for I, for A, then all you have to do is to multiply on the right by the inverse of that one. Now I have found my matrix. Finding my matrix. So now I have three matrices. Okay, so you give me three pairs and I can compute the matrix. What if you give me a fourth pair? Now you are very kind. And you give me another color, another color pair. And I do the same. So can I simply take this matrix, invert it, and I get A. Can I do that? I cannot. I know because this matrix, the new one, some size 3 times 4. To be invertible, you need that the matrix is a square. But it's not a square matrix, so you cannot invert it. Okay, so that is also another problem. That is, every pair is giving me three equations. I have three unknowns. So I have to, you give me three colors, what I have is 9 equations with 9 unknowns. So I can find the 9 unknowns. And now you are giving me 12 equations with 9 unknowns. So probably that will not be a solution. But there is not an exact matrix A that makes all the correspondences. The more points you give, the more colors you give, the less likely it is that you will find a matrix that satisfies all of them. So you can find something that more or less satisfies as much as it can. So if we format this time. Okay, so in general, there will not be a solution. So let's take to the equivalent. Okay. So let's say that you have two lines. This is second one. And one of these lines is a of x1 plus bx. So you see, the other line is bx1 plus bx2 is equal to f. So we have the same structure. We are solving two equations with two unknowns. So our unknowns are x1, x2. These are our unknowns. Then we have two equations with two unknowns. We can find a point where they intersect. But if I give you an extra constraint, I give you another equation. I give you another equation. Give you another equation. But all more or less close. So, but now they don't intersect in a single point. So can't you find a point? Okay, so there is, let's think again of this problem. So when you say this, the solution of that equation system, what you are saying is this point belongs to this line. This point belongs to this line. And so I have found a point that belongs to both lines. What about this one? This point. No. Leaving the key. Let's say that. That one. That one is not the solution. It is close to the solution. And I can measure. So why do I say it is not a solution? Because it is a little bit far from this line. It's a little bit far from this line, but the distance is not too large. The advantage of this point that the distance to each one of the lines is zero. This is not zero, but it is relatively close to zero. So this is not a solution, but it is close to a solution. Can I do the same here? Can I find a point that is not the solution of everyone? Because that is no solution. There is no solution for everyone, but it is more or less in the middle of everything. Can I find it? Okay, so how to formalize that concept? So what we want to find a solution now, our solution will be green. Such that, so how do we say it is almost close to everything? So we can say is, you give me a color. I will transform the input color corresponding input color. And this is the distance between them. It is difficult to using the square because it facilitates all the calculations. But this is the distance that we were talking before. This is this distance between the solution. And then what I want is that the sum over all pairs is as small as possible. So there is no solution. There is no hope that I can find a blue point that satisfies everyone. But can I find a green point that is close to almost everyone? And I have to minimize this respect to A. These are given data. This is given. My unknowns are here. These are my unknowns. I have to minimize this distance with respect to my unknowns. What is the name of this problem? There's a name. No, mathematicians are not very big. They have called it least. Because we are minimizing squares. Have you heard this before? This is squares? No. This is a very, very important. And the idea is this. So you cannot satisfy everyone. So you cannot make this go to zero. This distance go to zero. So I try to find a point, a matrix that almost satisfies everyone as much as possible. And the key is, okay, you will measure the distances between this is what we predict. So these are predictions. These are observations. So my model predicts that this color will be transformed into this thing. I want that my prediction is as close as possible to the observable. Okay, so there is a solution of this problem. The solution of this problem we will find some nice frequency. Okay, so let's rewrite our problem. Problem was, so I had a matrix of colors, and I had so I had input pairs of colors, and if you give me 3 colors, I can make them equal. If you give me more than 3 colors, I cannot find quality anymore, but I can try to find an approximation. I can try to transform these colors into a new set of colors that are as close as possible to these ones, and as close as possible in the least square sense. Okay, so let's put sizes on these things. So let's say that you give me n colors. Give me n colors. This is 3 times n. This is 3 times 3. This is 3 times n. So the equation is consistent, but I cannot invert this one. But there is a trick. So let's multiply by Pi transpose on the right. I multiply by Pi transpose. I will use equal for now. So multiply by this. Let's keep sizes again. This is 3 times n. This is n times 3. This is 3 times n times 3. So this multiplication is 3 times 3. This multiplication is of 3. Now you see the trick. Now I can invert this one. I can invert that. I will multiply by the inverse of that one. And so Pi minus 1. This is my A. And now I have solved my problem. I have found a way of calculating A. This seems to be kind of trick. So it turns out that this way to calculate A is this one. So when you try to find what is the A that minimizes this, is this one. So so and just for you to have names. This operation here, you know, is the inverse. This operation here is compensable inverse. So it is not an inverse, because an inverse is a very well-defined mathematical operation, but it works as an inverse. So you have this matrix here, you want to solve it, you want it to solve for A, so you have to turn it to the other side. And this is a nice way of turning it to the other side. And if you want to put more names, this is the pseudo inverse of mu. And again, the weight variable was an overclass. Okay, so now we know how to calculate the chain. Okay, so let's go back to the slides. This is what I'm putting here. So you have pairs. You have colors A, colors R. Have the matrix that transforms the color. This is the same kind of stuff I was writing before. Then I give up pairs. This is the least square problem. Transform every color in J to a color in I. And the problem was So I was writing in the other way. Both problems are equivalent, but instead of this is equivalent. So this is equivalent to minimize, so we can minimize instead of transforming I to look like J, I can transform J. Look like I. This is the one that is in the slides. So it is the same problem. So you want to transform J to look like I. The solution, and this is like all the reasoning we have improved here, the same kind of expressions. So it is the same derivation that I have done on the whiteboard, but now. Okay, so let's do it. So we have here our original image, our date image, and our graded image. Now we find correspondences. We put all the correspondences some matrix. This is here. These are our J and I matrices. Then I try to find A. Okay, so this with these correspondences, this is the transformation. Take this one, we make it like this. That is still is not the original. You can see this is better than the degrade. So the degraded lack a lot of glue. Now this is more glue, but still it is not. This one is not as good as this one. Okay, but this is because we gave just 3 correspondences. You can give more correspondences. Say these are same. You can give more colors, more pairs. The more pairs you have, the more accurate it will be. Then this one is better than the one just the pairs. Okay, so there are no questions. We can make the break now.